least we got the recorder on. And, oh, switching screen. Alright. Well, the weather is just getting a little bit warm these days, and the classrooms are already really hot. So I'm not really sure how we're going to deal with the summer when it gets here. Or the springtime, actual springtime. All right. So did you guys have any chance to read a little bit ahead of me? Okay, cool. That's good. Any questions about functions? No questions about functions. Not for now. Okay. So that's it's just a little slow. Zoom. Let's see, there we go. So my spare battery arrived for this computer because the battery that's in it is kind of old and it's not holding a charge the way it's supposed to. So I ordered a new battery from Amazon, and of course it's an off-brand. It's not from Panasonic, who makes this computer, and it didn't work. So I had to return it and try again. So this time I'm ordering something from Hong Kong. But this time it's supposed to be like genuine Panasonic parts and from eBay. So we'll see whether eBay beats Amazon in this case. All right, so let's go back to this class, 440. If there are no questions, we're going to start on relations. Okay. And I will release the function assignment, soon. Not right now. Come on. There we go. All right. So relations is a new note. So if it does have bugs or typos and whatnot, I'll go ahead and fix those. But for now, we're just gonna read the notes here. All right. So what a relation is there are. Okay. So first of all, terms. Okay. A relation is basically defining or telling you whether two elements of a particular set are related in a way or not. Okay. That's awfully vague, but that's exactly what it is. Okay. It doesn't tell you. A relation can be anything. So for this class, for the discussion of what a relation is, we are just going to say it is just relating two elements of a particular set. But the order is important, okay? So in other words, if you have a set that only has two elements, A and B, okay, whether A relates to B or B relates to A, those two relations are distinct. Is that okay? So that's important. So as a result, we know that in a relation, relation can be seen as a set, and that set is going to be a subset of whatever set the relation is defined over, crossing itself, Cartesian product with itself. And this is supposed to be a subset equal to, it is supposed to be just a subset, but not a proper subset of. So let me fix that first. Let me see if I can sign into my own computer at home and fix that. I cannot do that. Yes, the recording is already on. I cannot sign into my own computer at home, so I cannot fix it on the fly. But basically, if you want to make a note, there's supposed to be an underline here. So it is actually a subset of, but not a proper subset of. The symbol that is being used right now is proper subset of, which means R has to be smaller, quote unquote smaller, compared to the Cartesian product between x and x. So are we doing okay so far with this? Okay, so let's go ahead and make some examples. Um, for this purpose, I don't need to use my tablet because I think I can type a little bit faster than I can write. So what I'll do is I'm just going to use a text editor because most of the symbols that I need can be just hand typed. So we'll use this approach. All right, so I'll just use a random set. Okay, we'll call the random set x in this case, and we'll just define the content of x to be a, b, and c. Okay, so x is a finite. It's a set that has a finite number of elements a, b, and c, and that's supposed to be an equal sign, not a minus. There we go. I just mistyped. Now we can define a relation. Okay, so a relation once again is supposed to be a subset of the Cartesian product between x and x in this case. In other words, we're trying to define the relation R over the set x in this case. The simplest relation you can create, guess what? Is an empty set. It is still a relation, okay, because it is still a subset of the Cartesian product of x and x. Is that making any sense? Okay.
Just say that one more time.
In order for something to be a relation over a particular set, that relation has to be a subset of the Cartesian product of the set that the relation is supposed to be defined over, crossing itself, Cartesian product with itself. Well, an empty set is automatically a subset of every set there is. So it makes sense that the empty set is also a relation. It's valid as a relation. So later on, we'll also find out that even though the empty set or the empty relation doesn't say anything, it still has properties already. Okay? So we'll deal with that later. But for now, we'll go ahead and define the relation not as an empty set. So we'll get rid of this, okay? Because that's not very useful. It's not very meaningful. Let me see if I can improve the screen a little bit because I think it's cutting off the left edge just a little bit. So if I click auto setup, we'll fix it. Yep, it does. Cool.
Oh wow, it has a certified calibration.
Yeah, it's smart.
I'm watching you, Skynet.
Okay, so we can define a non-empty relation. I'm just randomly defining a particular element here. This is a relation. Okay, A relates to B. That's it. It has one single relation defined over a set of 3 elements, but that's okay, because I didn't say what R is actually meaning. I just say, okay, this is just random relation. But in this case, R cannot be a function, can it? It cannot be a function because what about B and C in the domain? It's not mapping anything to the codomain. But as a relation, that is not a requirement. You do not have to make every element relate to something. Okay, so this is perfectly okay as a relation. But you can also have something that looks like this. Okay, this is also a relation. Okay, you cannot have something like this in a function either, because in a function, everything from the domain you can only map something from the domain to the codomain once and only once. This is relating A to B, but it's also relating A to C. Not a problem in a relation. Is that okay? Yep.
So pretty much a relation is anything that matches in the second element. It has to have a relation with the first. So for example, A, B, and C is still a relationship. So
a relation is just a subset of the Cartesian product of X with itself. This is certainly a subset of X and X. The set that the relation is defined over. So let's go ahead and settle with this particular definition of R. So we can now talk about the other ways to talk about whether something relates to something else or not. So we can say A, R, B is true. Okay, if this is in fact how R is defined over X, then we can use this notation. We can use the infix notation, A, R, B, which means A relates to B through R, and that is true. We can also say ARC is true because AC is an element as a two-tuple inside R. But when we say ARA, it is false. A does not relate to itself. Yep.
And BRA
BRA
would also be false.
would also be false. Absolutely. So BRA is false because it is not. BA as a two-tuple is not in R in this case. Yes?
So I would say, so would CRA be true?
Hmm?
Would CRA be true?
What do you think?
No?
Is the two-tuple CA in the set? If it is not, then C does not relate to A. A relates to C, but C does not relate to A.
Vice versa about that. I'm trying to say that.
Well, because BRA is false,
Right.
it kind of follows that CRA would also be false.
So CD or BC would also be false.
Those would also be false. Yep. BRB is false. CRC is false. Okay. So if I were to spell out everything, including something, whether it relates to itself, how many rows are we talking about? 9 rows, exactly, because we have 3 elements. So when you look up, when you make it a table, you can say whether something relates to something else. So the size of the table is going to be it will be the cardinality of x times the cardinality of x. So the number of relations that can exist is the square of the cardinality of x in this case. Okay? So which ones are missing at this point? BRC, right, is false.
CRB.
CRA. CRB is also missing, right? And then CRA is missing as well. BRA is already listed. I think we got them all now. Okay, so we got AAA, BB, C, CC. Okay, so we got everything now. So is that okay so far? Alright. Shall we move on and talk about properties or certain qualifiers of relations? Okay, all right. So I'm gonna skip the concrete example because concrete examples are always kind of boring. I'm just kidding. So here's a random example that we just kind of went through. So now we are talking about the special properties of certain relations. So we'll talk about reflexive first. Being reflexive means that for every element in a particular set X, that element in itself, the two-tuple, is an element of R. That is what we need in order to define, to say that the relation over a particular set is reflexive. All right. So are there any questions about the casual definition of something being reflexive, or a relation being reflexive? Questions? Okay, well, we'll go through some examples now. So we'll go back to this one, okay, and we'll say, is the current definition of R reflexive? It is clearly not reflexive, right? Because where's ARA? Where's BRB? Where's BRB and CRC? Those are all needed. So I'm going to redefine R in this case. So we'll make a clean break from the one before. So these lines is basically just saying, okay, X is now, we're talking about a different problem now. So we'll still define X to be ABC, and then we'll define R to be something else, okay? Is R reflexive as it is defined right now? The A relates to itself, so is the relation itself reflexive?
Yes.
Okay, let's read the definition of being reflexive again. So if the definition of reflexive is instead of for all, if it is there exists, then that particular R would have been reflexive. Unfortunately, because the quantifier is a for all, that means if you pick any element out of X, that element has to relate to itself. In the example that we had, what about B and C? Those are all elements of X, but they do not relate to themselves. So in this case, this is not reflexive. Okay. What about this R then? If we redefine R so that we have AA, BB, and CC, would that be reflexive? Definitely. Okay? So this is reflexive. What about this one? We got AA, BB, CC, and I'm going to throw in AC in here. Would that be reflexive? Does it still meet that requirement that every element in X relates to itself? They still relate to itself, we just have some extra stuff here. So it will still be reflexive in this case. This is still reflexive, not a problem. Is that okay? Sure. Then it will not be reflexive because C as an element of X does not relate to itself. So that really kind of goes back to the definition of the quantifier of for all. So it is important that we understand the quantifier for all because we're going to use this for the entire semester. So we got to get those terminology there. All right. Any other questions? Okay. So we're going to move on to a symmetric relation. Now, by the way, a relation can be symmetric and reflexive at the same time, but we're going to focus on being symmetric. So being symmetric means if you choose any two elements from X, okay? If EF is in R, EF is in R if and only if FE is also in R. That defines reflexivity. No, take that. Symmetry. That defines symmetry. Okay, but that is kind of strange. Okay, so we'll use an example. We'll use several examples to illustrate whether a particular relation is symmetric or not. But before we move on, are there any questions about how symmetry is defined? For every E and for every F in a set that relation is supposed to be defined over, EF is in R if and only if FE is also in R.
So kind of like when a relationship between two elements is
if one exists, the other one has to.
yeah, and it has to exist by
Yeah, but if one does not, then the other one should not either.
Oh,
Okay? Yep.
You made a typo. That definition says
Yeah, this one here. This is supposed to be symmetric. But I can't fix my notes right now. For some reason, my DDNS is not set up correctly, so I cannot get back on my. So DDNS stands for dynamic DNS. Okay. So let's go ahead and check out a few examples. Okay. This is called being symmetric. So cross out this term and make it symmetric. Okay. If you look up the definition of symmetry or what relation are considered symmetric, some definitions will use this and some other definitions will use something else. So there are multiple ways to express whether a relation is symmetric or not. Some people would just make it easier to read, so they would say E, R, F, if and only if F, R, E, which means exactly two. Okay. All right, so let's go ahead and take a look at a few examples and see whether those things are reflexive or not. So I'm going to break from this again because this is a different discussion. I'm going to continue to define X to be A, B, and C just because we are now used to it. So we'll start with the simplest one. R is empty. Is it symmetric?
Yeah.
Okay. So for those of you who say it is not reflexive, why is it not symmetric? Why is it not symmetric? Not reflexive, we are talking about symmetry now. So is it symmetric? Huh? But that's okay. Because if you use that definition, AA should be there only if and only if AA is there. Okay, but since AA is not there, the if and only if is actually true. Okay, so let me explain what I mean by that. Okay, so we'll say, okay, we'll evaluate that whole thing and see if it is holding true for every single element. Yep.
So it's like tilde XOR?
So
It's like tilde XOR?
it is XOR in a
Like the
strange way. It's the opposite of XOR. Yeah, it's a not XOR. Yep.
So AA itself is not very symmetry. It does depend on the
AA is not needed for symmetry. You're correct.
I mean, if AA is there, it does not break symmetry of itself because it doesn't need a
If AA is there, it will still be symmetric. Yep. If AA is the only thing in there, it will still be symmetric. Okay, so let's check out, how we qualify this whole thing to be symmetric or not. Is that okay? All right. So good thing I chose two different letters in the definition, so we can now use the EF here. So we say ERF, okay, and then we say FRE, and then we say ERF, if and only if FRE. So we're going to evaluate all of these expressions, okay? Not the E and F are elements to be in X. So this is going to be a little bit tedious. It's not that bad. It's not as bad as you think it is. It's only bad for me. It's not bad for you because I'm typing it. You guys are just watching. But that gives you time to kind of think about this a little bit. Okay?
Is this random or you randomize this or?
What do you think? Does it look random to me?
Just making sure that I second guess myself a lot. I'm just making sure.
Well, I mean, okay, if it's not random, what makes this not random? The way I put the values under the E column and the F column. I go through, so E is stuck with A first, and then F goes through all the possible values. E moves on to the next, and then F goes through all the possible values. C goes through the last possible value, and then E goes through every single value. Yep.
Well, it could still be random though. Maybe we just start really
That is possible. But this can be, okay, it may still be just random, it's a random process in my head that somehow generate this. But it also so happens that you can have a nested loop that can generate this. How about that? So yes, it may be random, but at the same time, a structured program can generate this as well. Okay, so now we ask the question. This is pretty easy, right? Is that true or not? No, it's false. How about this? False. The relation itself is empty. It is false for everything. So now the question is, false, if and only is false, is that statement true? Okay, so that is the key. And it's the same for every single row. So now I can do it a lot faster than you possibly can on a piece of paper. Okay, I'm done.
An arrow and go down.
Yeah, dot, right?
Yeah.
Yeah, but this is why. Okay, so but the bottom line is this enumerates every single way for me for any element in X to relate to any other element in X, right? It enumerates all the possibilities, and yet the statement that we're looking for is true for every single case. So that means this relation, which is empty, is symmetric. As odd as it seems, okay, an empty relation is symmetric. It's almost like you have nothing, and then you have a mirror, and if the other side of the mirror also has nothing, is this mirror working properly? Yep.
I would hope that said there is nothing.
Huh?
I would hope that said there is
So are we good with this one? All right. Okay, so let me continue to make this one a little bit bigger, and then each time I'll ask you, is it symmetric? So now I'm going to introduce a single element here, AA. Okay? It is not reflexive because B does not relate to itself, C does not relate to itself. So forget about being reflexive. We're not focusing on being reflexive. We're only focusing on is it symmetric. What do I have to change in the table? I got to change one row, right? A relates to A. Okay, change this to 1. A relates to A. So now the question is, I'm not done, okay, because this is a question, should I change this one? Okay, true, if and only if true is true itself. Okay, but the rest remain the same because, other than A relating to itself, there are no further relations in the set. So that means, this particular relation, which only has one single element, is also symmetric. Is that okay? All right? So what makes it not symmetric, right? Okay, so let's see how we can make it not symmetric. Yeah, not symmetric is pretty easy because you just have to make it lopsided. Okay. That is not symmetric anymore. But we want to see why it is not symmetric. Okay? So if AB is in the set, okay, then A relates to B, B, R, F is a 1. But B relates to 1 is still false. That one is missing. So now, when we reevaluate the if and only if, now we have true, if and only if false. That is false. Okay? So that is why we can now say, hey, look at this column here. At least one item here is a false, so the entire thing is not true anymore. This particular relation is not symmetric. Yep, go ahead.
So there'd be another false.
This is another false.
Or is not really the end.
Oh, right. You are correct. So B, R, A is false, but A, R, B is true. But that will also make the result here to be false. Thank you. Very good. Yep.
Would this be a case where you run over the first case and you don't find the second case?
When you run over the
Like
first
if you have a list or something and you have one of them that you see the relations the relation of, but then you don't see the counter.
That's correct. That's exactly what we. If that is missing, that will make it not symmetric. So are we doing okay so far with this? Okay. So let me emphasize that this is not symmetric. The other two are. This is not symmetric. All right. Just one more example, and then we'll move on to the next one. So I'm going to reuse this example here and cross out the conclusion. And then we'll say, what about if I put this back here? If I add BA in here, how is that going to change the truth table? If B is going to be true again, but how is it affecting the truth table? This becomes true now, and that becomes true now, which also means if you look at the last column, this is now true, this is now true, so everything in the last column or the rightmost column is true, and as a result, this relation is symmetric again. So we do okay so far, looking at these examples and understand how we define symmetry in relations. Okay, all right, cool. All right, so we have 2 more to go, and then we can start to think about some complex interaction between these. So the next one is called transitive, which is not unlike the transitive stuff that you see in normal algebra. So this time we look at 3 elements, randomly picked from the set X, okay? So we pick E, F, and G as elements in X. They can be the same, they can be different, but this time we have to look at every single way to pick any 3 elements out of X. The statement is no longer if and only if. It is just an if in this case. It only implies. what it is saying is ERF and FRG implies ERG. That if you can say that is that whole thing to be true, if you can say that this side is true for every way to arrange three elements from R, then we can say that R is transitive. Is that okay? So this time I can give you an example, but I'm not going to use three elements, because if I use three elements, the table is going to be 27 items long, because it's going to be 3 times 3 times 3. Because the first element E has 3 possible values, the second element F has 3 possible values, the last element G also has 3 possible values. So we have 3 times 3, which is 9, 9 times 3 is 27. That's a really long table, and it is kind of unnecessary to be that long. Well, it is kind of necessary, but this is a tough one. I'm just thinking of whether I can, how I can generate all of these examples and make it easy to visualize. That's what I'm thinking. Or I can just give you examples. Okay, let's go through just examples first. Okay, if you guys have questions, then we'll go back and see if I can enumerate all the possible cases, or at least the cases where it is important. Okay, so let's put a dotted line here. And now we're moving on to being transitive. So we'll define X to be A, B, and C again. And this time once again, we start with the empty relation. Okay. So the question is an empty relation automatically transitive or not? So you boil it down to the question. Okay, if I pick any 3 elements from the set, okay, not necessarily different, just pick any 3 elements from the set. Can I claim that this expression is true? That is the question. Can I claim this is true for every way of picking 3 elements out of X? But the relation is empty, remember, okay? So now the question you have to ask yourself is, well, I only have something to worry about if I can make the left-hand side of the implication true. Because if the left-hand side of the implication is false, the whole thing is automatically true, and you don't have to worry, right? So the question is, can I find ERF for any case in this particular set? The answer is, we talked about an empty relation, so nothing relates to anything, right? Not anything else, not even itself, right? So that means the left-hand side of this conjunction is false to begin with. Do I have to look at the right-hand side and evaluate the right-hand side of the conjunction? No, we can use short circuit evaluation, because if the left-hand side of the conjunction is false, the conjunction has to be false anyway. Well, wait, hold on a second. The whole conjunction is the left-hand side of the implication, which makes the implication itself true. Whoa, we're done. We have just kind of casually proven that an empty relation is automatically transitive. Is that okay with everybody? Okay. Okay, so then we can look into some, so I'll just say this is transitive. Okay. What about this? Is that transitive? It has only one thing in it, okay? Just AD. Is it automatically transitive? It is transitive. Why is it transitive? Okay, so let's remember this. Okay, just remember this is how we define relation R, and then we'll go back to the definition. So you look at this thing here and go like, okay, how is the left-hand side of the implication always false? Why is this always false? Yep.
So there's only one element. So in this case, B would be F. So there's nothing B
So if you make one of these true, the other one has to be false. Yep. So that means the conjunction itself is always false, but since the conjunction is the left-hand side of an implication, if the left-hand side of the implication is always false, then the implication itself is always true. We're done. Cool. Are we doing okay so far with this? All right. Let's look at this one then. I'm going to throw in one more thing into the set. Is that transitive? We got two elements now in the relation. Is it going to be, is this transitive? It is still transitive. Because I just have to say A is E, A is F, B is G. Okay? So in that case, the entire left-hand side of the conjunction would be true. ARA is true, ARB is true. But then you pick out E and G. E is A, G is B. Is ERG. ERG is true, right? So you have true implies true, which makes it true. So the whole thing is still true. But there's no other way to instantiate your E, F, and G so that the left-hand side of the implication is true. So for the rest of that entire table, for the other 26 entries of the table, they're automatically false. Is that okay or not?
So how do you make it false?
How do I make it false?
Yes.
How do I make what false?
So it won't be transitive.
How do I make it not transitive?
Yes.
Okay, so I'm going to say this is transitive. So if I define A, B, and B, C, now it is not transitive. Why is it not transitive? Well, because if E is A, B is F, and C is G, then you make the entire left-hand side of the implication true. But then is A or C? Nope, A does not relate to C, so the right-hand side of the implication is false, while the left-hand side is true. So now you have true implies false, which makes the implication itself false. Well, even though that is the only item, okay, that is false, you only need one thing to be false to make this relation not transitive. So the answer is this one is not transitive. Yep, go ahead. It makes the left-hand side true, but it makes the right-hand side false. Because A or C is missing from the relation. Which brings us to the last item. How do we make this transitive again? So R is AB, BC, and all I need to do is to add AC to the whole thing. Now it is transitive again. Is that okay? Are there any questions about whether a relation is transitive or not?
As long as there's a between
Not as much that. It is basically saying as long as so as long as if E relates to F and F relates to G implies E relates to G for every way of picking three elements E, F, and G, then the relation is transitive. So other than that, it's really kind of hard to describe, what makes it, what makes a relation transitive. Go ahead.
So in the last relation, is it A and B that's going to be E and F, B and C is F and G, and then A and C is E and G?
So if you pick A to the E, B to the F, C to the G, that row is going to be true.
Okay.
Yep. Go ahead. Just AB and AC, that would still be transitive. That would still be transitive because the left-hand side of the implication is always going to be false because you cannot, um, there's no link element per se, because, in this case, in the case of AB, BC, AC, I just term, B as a link element because it is the second element of one relation, and yet it is the first element of another relation. So it becomes quote unquote a link. But if you cannot have any link elements, then it doesn't even matter what the rest looks like because there's nothing to link to. Yep.
So with AC, so like we put at AC and we had AC and then we had AC, that's still be the same thing.
Say that one more time.
AC, or so let's say that we go to the second one, not the second one, last one, where it says A, B, C, and it's transfer, right? What's up between that A, B to AC, that's still,
Okay, which are we talking about this one or this one?
the last one,
The last one here.
and then the first element,
B.
yeah, that was AC.
Then it would not be a set because you have AC and AC, they are duplicates.
Or let's say that we switch AC.
Did we get rid of this one? Okay, so you're basically saying about, talking about removing AB from the set.
Yeah, and
Right?
then put AC from the DC, that's what we.
Well, okay, position does not matter in a set. So you're just saying, okay, we're removing AB from the set is enough because there's no ordering within the set. Okay. Now what do you think? If the relation, okay, let me just write it out so it becomes clear. Okay. Because I want you guys to think about this and figure out, is it transitive or not? So we are basically talking about removing this guy out, okay? Which basically takes out, there's no link element here anymore. So the question is this transitive or not? Okay, so forget about this is transitive, we are not asserting it yet, okay? We're questioning, is it transitive or not? And what do you guys think? It is transitive because the left-hand side of the implication is always false.
You said it.
Huh?
What do you mean on that?
The left-hand side is always false in that case. Oh. I'm looking at, we're looking at this one. There we go.
In the last relation, it's the right hand side is true.
The right-hand side can be true, but the left-hand side is always false. We know the left-hand side is always false because we cannot find an F that is basically a link element. Because there's okay. Let's go back to the example here. If you look at A, B, and C, none of them is in a position where it is the second element in one two tuple, but it serves as the first element of another two tuple. We cannot find such an element. If such an element cannot be found, we have no link elements, then the relation is automatically transitive because there's no question of whether it is transitive or not. No one is serving as a link. Yep.
For what's A, B, C, AC? So remember it's AC and CA.
Then it would not be transitive. It has to be AC because the ordering is important. Now, if you flip the other two, then it would be okay.
So BA, CB.
Exactly. Now, if you flip if you flip the first one to DA, the second one to CB, and the last one to CA, then it would be transitive again. Yep. So, let me just answer this question here. This is, in fact, transitive. So we good so far or not? Okay, cool. So now we move on to anti-symmetric. So anti-symmetric is kind of really Interesting. There are several ways to define it too, but this is one definition. So antisymmetric means a relation R over set X is transitive. Oops. Obviously I copied and pasted a little bit too much. This is supposed to be antisymmetric. So cross that out and turn it into antisymmetric. So a relation R over a set X is antisymmetric if and only if the following condition is true. The condition itself is actually correct. Okay, so the term is incorrect, but the qualification is actually correct. So let's focus on what is inside here. For any two elements EF that you can pick from X, the following has to be true. ERF and FRE implies that E equals to F. They are the same thing. And this is called antisymmetric. That's how it's called. So you can read the next sentence. It says right there, okay, the definition is also true for any empty relation. Why do you think it is true for any empty relation, where the R is an empty set? Yep, because the left-hand side of the implication is guaranteed to be false. You cannot find any relation whatsoever. Nothing relates to anything in the set. Well, that makes the left-hand side false, right? If the left-hand side of the implication is false, then the implication itself is true. So since this whole thing, the implication is true for any pair of elements that you can pick from X, then the relation is in fact antisymmetric. Is that okay? So let's go ahead and take a look at a few examples. Okay. So this time we are focusing on whether something is antisymmetric or not, or antisymmetry. So once again, it is important to define what the relation is defined over, because by changing X, you can make a relation. You can change the property of a relation. All right. So this one is in antisymmetric. Okay, because we just talked about it. Okay. So we'll look at a simple one. What about just that? Is that antisymmetric? Got yes and no. Well, unfortunately, in a class like this, it cannot be done by voting. So we have to actually talk about which one is true. Which is the only thing that is separating me from being Eliza. Eliza. Okay, so how would you guys like to have Eliza as your professor?
I don't know.
Okay, so look it up, and you guys can read the rest later. So ELIZA is a natural language processing computer program, and what it does is an approach, is an attempt, okay, to make something pass the Turing test, okay. But ELIZA is a very simplistic program. If a computer back in the 60s can do this, it is simplistic, okay. Because my Fitbit has got more processing power than most computers in those days, like a whole room full of computers. I have more processing power on my wrist right now. And that's without even relying on the Bluetooth to hook up to the web, to the cloud. Okay, so ELIZA is basically just keep asking questions and replying, but it knows how to pick out keywords from a sentence. So whatever you say, it will ask you something about it. So like when you ask me, so what if I do this to the relation, is it symmetric or not? Then I'll just kind of throw the question back to you and say, what do you think, right? So that's the ELIZA approach to teaching the class.
It's Skynet.
Well, if Skynet is ELIZA, I got nothing to worry about.
But if nobody says anything, does Eliza teach anything?
If Skynet runs on Windows, I also got nothing to worry about.
Oh no, I'm gonna die.
The only thing I worry about is the Chrome dropping on me because it wants to reboot like 6 times in an update. Mid-flight, it's like, oh, Windows got an update. I'm just about to shoot Professor Tag, right? Update.
They heard you.
They heard me?
Yeah, probably. No, they're too
Meltdown.
updating.
Okay, so question now is this relation anti-symmetric?
Yes, both sides are true.
because we just say E is A, F is A, right? Okay, let's see what happens when E and F are both A. So if E is A, F is A, can I say E, F is in R?
Yes.
Can I say F, E is in R? That's a stupid question. Okay. Does A equal to A?
Yes.
Okay. So that row is true, but what about for all of the other rows where at least one of E or F is not A? Well, the relations do not exist for those combinations, right? Which also means, these conjunctions, each side of the conjunction has to be false when E and F are different, okay? Or at least one of them is not A. Is that making any sense? So if that is false, that means the entire conjunction is false. But when the conjunction is false, the implication is true. So for the rest of the table, everything is true as well. So that means that particular relation is in fact anti-symmetric. Is that okay?
But then it's symmetric as well.
Hmm?
But
It is not. It is also symmetric. Yes, it is both symmetric and anti-symmetric at the same time. Yes. In fact, if you look at symmetric versus anti-symmetric, the main difference is if something is already symmetric, then what you're looking for is when it is for the rows where the left-hand side is true, are we talking about the same element? That is the question.
Mm-hmm.
Okay, so that means I can now, okay, this is anti-symmetric. Okay, so let's take a look at this one. So we got A, B, all by itself, okay? Is this anti-symmetric? It is anti-symmetric because at least one of the conditions in the conjunction is false, which means the entire conjunction is false, which means the left-hand side of the implication is false, which means the implication itself is true. So this is, in fact, anti-symmetric. What about this one? Now, first of all, this one is symmetric, okay? But is it anti-symmetric?
No.
It is not, because A R B, true, B R A, true, so A R B and B R A, but is A B the same?
No.
Nope. So we have false. We have true implies false, which means for that row, the implication is false. Well, we just need one row where the implication is false to make the entire thing not anti-symmetric. So this one is not anti-symmetric. So is that okay so far? So we got reflexive, we got symmetric, we got transitive, and then we also have anti-symmetric. Okay, so those are the four qualities of relations. So now we can move on to partial ordering. Okay, so partial ordering is really just lumping some of the things that we have already talked about and say, hey, if these things are all true, then we say that relation is partially ordered. So we basically define a set X is to be partially ordered by a relation R if and only if the following is true. Okay, so we have three things that have to be true at the same time in order for R to be considered a partial ordering kind of relation. R, it has to be reflexive, it has to be anti-symmetric, and it also has to be transitive. Okay? So if R satisfies all of these requirements at the same time, then we have partial ordering. Is that okay? So the question now is, okay, fancy terms, right? Partial ordering and stuff like that. So now the question is, what is that going to buy us? So in order to illustrate, a non-trivial case of a partial ordering type of relation, we'll look into a beer commercial. I'm not sure how many of you remember the beer commercial. I think it's a non-American beer. And in the commercial, it says, it's good to be rich and smooth at the same time. You guys don't remember that beer commercial?
The Super Bowl commercial?
No. It's a commercial. It's a typical. Okay, let me see if I can find it on YouTube. What year? Not that long ago. I don't think it's that long ago. Okay. And I don't even drink beer. But the commercial stood out in my mind because it's like, hey, I can use this in a logic class. Okay, come on. There we go. Rich and smooth beer. Let me see if I can hook up the sound. It's really kind of funny. Actually, if it has closed captioning, then it's still just as good.
Yeah, it's funny. Yeah, maybe I want to hear more Freeman's voice. Oh, I
Okay. So I'm gonna roll it back all the way to the beginning. There you go.
It's covering the captions.
It's square.
Move your mouse.
Oh. Sorry. So smooth,
Now I remember this.
but not rich. So you want your beer to be smooth and rich. Okay, you guys don't remember this?
I do now. No.
You never looked at it from the logic perspective then.
We don't watch normal television.
Okay, so how does that relate to this class?
After you do this, you're going to want a nice cold one.
Okay.
A nice cold one right now.
Most people do after 440. I don't understand why.
Pull out a whole chest of root beer.
Okay. So such an ordering is not uncommon. Okay, so we're going to define the relation called more desirable than. I thought I changed that a little bit. Okay, there we go. Okay, so more desirable than is more desirable than is a relation. Okay, but this relation is not. Okay, it is not a partial ordering because it's not reflexive. Does that make any sense? It's not reflexive. It does not relate to itself. Okay, so what are the elements of this particular set? There are 4 elements in this particular set. The first element is not smooth and not rich. One element. Smooth but not rich. Another element. Not smooth but rich. Another element. And the last element is smooth and rich at the same time. So we got 4 elements. So we want to find out, okay, is this relation is more desirable than, is it reflexive? It's not reflexive, okay? Because smooth and rich is not more desirable than smooth and rich. It's missing, so it's not reflexive. And as a result, that relation is not a partial ordering relation. Okay, fine, let's redefine the relation a little bit. Because the flip side of that is, so that's why I have this kind of, it looks like a typo, but it's not. Alada. So alada is at least as desirable as. Okay. So I just redefined it a little bit. So now we have a reflexive relation because rich and smooth and rich is at least as desirable as smooth and rich, right? Smooth and rich is at least as desirable as smooth but not rich. Smooth and rich is at least as desirable as smooth but not rich. And smooth and rich is at least as desirable as not smooth and not rich. Is that okay? Then we move on to smooth and not rich. Okay? Smooth and not rich is at least as desirable as smooth and not rich to itself, right? And then the next line says smooth and not rich is at least as desirable as not smooth and not rich. But it does not relate to not smooth and rich. Because it's a toss up, okay? Because you're missing one, but you got the other. Okay, so there's no relation between those two. Not smooth and rich is at least as desirable as itself, which is not smooth and rich, But it is also at least as desirable as not smooth and not rich, because that's the least desirable to everything else, right? And then the last one is not smooth and not rich is at least as desirable or undesirable as not smooth and not rich. It relates to itself, but nothing else. Nothing else is worse. Is that okay? At least in the beer commercial, right?
What about nothing?
Hmm?
Would that be on the list next to them?
Nothing?
Right.
No, because it has to be one of the elements. Remember, our set has 4 elements. We're trying to figure out what element in the set relates to another element of the set. So now the question is this relation reflexive? Is each element relating to itself? Yes. Okay. Is it transitive? Remember what transitive is? Okay. No. Okay. Which item or items serve as link elements? In other words, it is the second item of one relation, but it's the first item of yet another relation. Smooth but not rich is one. Not smooth but rich, they are both link elements. So now we have to figure out, okay, but is this relation transitive? Okay, let's check. Smooth and rich is at least as desirable as smooth but not rich. So that makes smooth but not rich a link element at this point. So we'll check out smooth but not rich as the first item. Smooth and not rich right here. Okay, let's pick this one. Is at least as desirable as not smooth and not rich. Okay? So now the question is, can we skip the link element and directly connect the first to the last? In other words, is smooth and rich at least as desirable as not smooth and not rich? You go to the list, it is right here. So it satisfies the requirement of being transitive. But there's another transitive relation of going through smooth and not rich. But it is transitive, okay? The relation is transitive. What was the last one? Anti-symmetric. So is this relation anti-symmetric? So what you do is you look at everything that is symmetric, and then you say, oh, when it is symmetric, it is actually talking about itself. Okay. Rich and smooth and rich is at least as desirable as smooth and rich. Well, it is relating to itself. Okay. And then you have smooth and not rich relating to itself, and then you have not smooth and rich relating to itself, and then you have not smooth and not rich relating to itself. But you do not find anything else that satisfies the symmetry requirement, but yet it is not the same element relating to itself. So that makes this relation also anti-symmetric. That was a kind of earlier. Answer the question. No? Possible. Okay, so this is actually a partial ordering type of relation. So at least as desirable as, in this particular definition is partial ordering. Now, partial ordering means it is not always possible to say whether something relates to something else or not. Okay? Like in this case, do I know whether smooth and not rich is at least as desirable as not smooth and rich? It's not listed here. That relation is never established. In other words, if I were to ask you to sort the 4 elements in this particular set, you cannot sort it linearly. Because there are 2 elements here where the ordering is undetermined. You cannot say, oh, we have to put this one ahead of the other one. Nope, because nobody tells you which one is supposed to be ahead of the other. Does that make any sense? So we call this partial ordering. Now, partial ordering actually is a problem more frequently occurring than most people think. Okay, it is a problem when you have ways of comparing that you can establish certain types of ordering, but not completely ordering everything. Okay, which is illustrated by this example. Smooth is good. Rich is good. But if you're missing one, how do you compare missing this one versus missing that one? It doesn't tell you. Okay? At least in the context of the beer commercial. I'm sure some individuals have their own answers. Is that okay? All right. So if you can, okay, if something is called partial ordering, what do you think is going to be the next topic? Even if you have not read the notes ahead of time. Total or complete or something along that line, right? Because if there's a partial, that means, hey, maybe something is actually not partial. So yes, in fact, there's something called a total ordering. So if you look at the requirements for a relation to be total ordering, a total ordering relation over a particular set R, set X, it has to be reflexive, we got that. Antisymmetric, we got that. Transitive, we got that. But then it has one extra requirement that has no name that we have used so far. It actually does have a name, it's called trichotomy long, okay, but we haven't really mentioned that. Okay, so instead of using that term, we'll just look at what does it mean. It's basically saying for every E and F, if you pick any two things out of X, okay, you have to be able to say E or F or F or E. Now, this is not exclusive OR, this is a regular OR, which means at least one of these two relations has to exist. Yep. There's no implication in this requirement. In other words, the OR is the only thing that has to be true, which means one side of the OR, at least one side of the OR has to be true. Which also means, hey, for every two things you can take out of the set, they have to be related, one way or another. That's basically what it's saying. What if I'm picking the same thing? What if E and F are the same? That is covered already by being reflexive. So no need to worry about that. Is that okay? So by adding this last requirement, then we have total ordering, which means if you give me any two things in a set, okay, I can tell you how they're supposed to be ordered. If you give me the same thing, I can tell you they are the same, okay, so they're right next to each other. If you give me two things that are not the same, I can tell you how they're supposed to be ordered. Does that make any sense? So far so good? Okay, so I want to relate this to programming concepts, okay, because if I don't relate things to programming concepts or practical examples where you can use it in daily life, in daily programming, then this class is not really that valuable. So think about overloading the less than or equal to operator in C and C++. You guys know about overloading operators, right? You can just redefine an operator and like, okay, this is how I define something. So let's just say you define a class, of gamer, okay? And gamers have a lot of attributes, right? I'm just picking, out of a list of things. You can rank a gamer based on how much time they spend, right? How much money they spend. How many people they friend them, okay? How many games they have won. What is the, is it called kill ratio? Yeah, kill death ratio, KDR. How often do they assist? What is the assist ratio? And so on and so forth, right? There's many individual numbers, okay? And each one can be used for in its own ranking. So if you are to pick the top player of the year, okay, a top player of a particular team, how are you going to do it?
Yeah.
I see, I get it. Okay, so the CA is just the money. Okay, but you can see the problem, right? Okay, so if somebody is spending less time online, spending less money online, have fewer friends, a lower KDR, and in every single category, worse than another player. The ranking is easy to do, right? Because that person, Everything we can put a number. This person is not as good as the other person. Okay, the ordering comes easy. What if it is not like that? What if one person outspends the other person, but one has more friends, and even from the game publisher perspective, friend is important because that's how this person can draw other people into the game. So even though this person may not be directly spending a lot of money, the people this person brought into the game may be spending money, right? So what if you have a situation like that? Some loaner, okay, some billionaire loaner decides I'm gonna just spend money, buy everything, okay? But I have no friends. In fact, I only have enemies. Okay? And then another person goes like, I'm broke, okay? I got no money.
That's me.
But I got a lot of friends, and they help to spend enough money, and they fund my games too, okay? So how do you rank those two now? Because you got two numbers, and one person has one number being greater than the other one, and opposite, when you look at a different metric. So you have partial ordering again. Do you see it? Do you see what I mean? So when you have partial ordering, and if your task is to say, okay, I need to name the top player of the team, the school, the country, or whatever, now you have a problem because you cannot rank anymore. So you need total ordering. But in order to do total ordering of these gamers, you have to come up with a different metric and say, how do I break these so-called, they're not ties, okay? You just have to say, okay, how do I combine these numbers to a single number where it can be compared? Yep.
They kind of like look at the growth potential, because like if it's just a single billionaire guy, but he doesn't contribute to any like growth potential for a game, then like his value could be a lot less than somebody that's broke, but can influence other people to play the game as well, which the community would grow.
Possibly.
If you value players' growth.
Well, the bottom line is revenue. So basically, so in the case of let me answer your question first. Go ahead.
I mean, wouldn't you just basically have to make a choice? Like, at some point, you just have to make a choice which one is more important to you.
Right, the gaming company has to make that choice, but whatever the choice is, it has to be represented by a relation, right? To get back to the topic that we have here. So in the case of programming, when you overload that less than or equal to, which means this player is quote unquote worse than or the same as the other player, you have to define that operator in the sense that it is defining a total ordering so they can sort. Because a partial ordering relation is not may not be able to sort. It may have elements where you cannot say, okay, is this supposed to be ahead of the other one? They are not ordered. Yep, go ahead.
So in terms of either spending or the amount of friends, you have to set like which one is greater, the spending or the amount of friends in a certain category by condition.
So the bottom line to a game publisher is which one is more beneficial in the long run to the game company. Now, how you come up with that number by combining everything else, that's a whole different story. But the one bottom line is, whichever player can bring the most benefit to the gaming company or the game publisher is the one that you want to name as Gamer of the Year. But it's one single number. You cannot have fragmented and have all of these 6, 7 different numbers and say, okay, how do we compare when we have all of these different numbers? You have to consolidate everything to a single number. Because with a real number, the less than or equal to relation itself is a total ordering relation. So I kept this to the last because if I had said, oh, less than or equal to is total ordering, then you guys would just go like, oh, less than or equal to, that's really the only thing you remember. So that's why I kind of left it to the last and go like, oh, by the way, there's a real life relation called less than or equal to, and it is defining total ordering. Yep.
Wouldn't those numbers also change with respect to short-term versus long-term goals of the company? Because like those numbers in short-term could look really good, or like in the long-term it could be.
But you have to remember, short-term goals is also a part of the long-term goal. So you cannot sacrifice short-term goal You cannot sacrifice long term for short term. You can do the opposite, but you cannot sacrifice long term for short term. Yep.
So could you like create a variable that gets updated for all the stats of one player and then compare that?
You can either use an equation of some kind or you can use some kind of model, but the bottom line is you have to come up with one single number in the when you use it for sorting the ranking of players.
And then you compare that.
Right, because with real numbers, the less than or equal to relation is total ordering. Wait, I just said something that I did not actually go through and analyze, right? So let's double check. Okay, so think about x in this case as integers or real numbers. It doesn't matter one or the other. It does work. Okay, and r is less than or equal to. Okay, so is it reflexive? Is every number less than or equal to itself? Is it antisymmetric? If A is less than or equal to B, and B is less than or equal to A, does that imply A and B are the same thing? Yes. Okay, makes sense, right? Is it transitive? If A is less than or equal to B, and B is less than or equal to C, does that imply A is less than or equal to C? Yes. And the last one, which is really important for something to be total ordering instead of partial ordering. If I give you any two numbers, okay, is it always true that at least one of these two is true? A is less than or equal to B, or B is less than or equal to A. Doesn't matter what A is, doesn't matter what B is. At least one of these two has to be true, right? So we know that less than or equal to as a relation defined over integers or real number is a total ordering kind of relation. And that is why if you want to rank gamers, you have to consolidate all the stats, everything into a single number. If you can do that, then you can rank the players. But if you cannot, then your ranking may not actually be useful. Is that making any sense? So we do a lot of stuff like this, when even when you are evaluating eBay sellers, right? Shipping, okay? This sellers ship fast all the time. Yes. But is the item always as described? Sometimes. Okay, sometimes not. So once again, you have to consolidate all of those stats into one single number. Then you can name, okay, this is the eBay seller of the year. But if you cannot, and you have all these different numbers and stats, then it is the best you can do is partial order in that case. All right. So please read ahead of me. We are pretty much done with relations. I will get the function assignment up and running at latest by Wednesday, and then we're going to move on to the next topic. Yep. Say again. Olive, no. Yep. So read that one. It's a fun one. Long too. All right. Let me turn on the recorder.